Again, welcome back to calculus. This lectures cover the chain rule. So we start with two examples. Our first question is, we should find the derivative of f at x equal to 2x cubed minus 5x squared plus 4 to the power 5. Now, looking at this question, we cannot use only the power rule to solve this problem. That's to find the derivative. Also, we cannot use either the difference or the sum rule alone. So the concept to use in order to solve this problem is the chain rule. So the chain rule means we are going to use the power rule, to find the derivative of 2s cubed minus 5s squared plus 4 to the power 5. Then we find the derivative of 2s cubed minus 5s squared plus 4 and multiply both together. So this will be the solution here. So first, using the power rule, we get 5, 2s cubed minus 5s squared plus 4 to the power 4, because 5 minus 1 is 4. Then we find the derivative of 2s cubed minus 5s squared plus 4. And that will give us 6x squared minus 10x plus 0. Then we multiply both together, so multiplication. So our final solution will be 5 times 2s cubed minus 5s squared plus 4 to the power 4 times 6s squared minus 10x. And that's our final solution. So this is again the concept of using a chain rule. And later on, we are going to talk about the reason why we use a chain rule. And for example, here, the main reason is that this is a composite function. Also, we can see the second example, the same concept again. This is a composite function. So in order to find the derivative of this function, first we need to use the power rule to find the derivative of 1 over 2t plus 1 to the power 4. Then we find the derivative of 1 over 2t plus 1. So we can rewrite this function as 2t plus 1 to the power negative 4, the reciprocal. So it's the same question here. So we have 2t plus 1 to the power negative 1 and to 4. So this will give us again 2t plus 1 to the power negative 4. Again, straightforward. Since this is positive 4, we can just find the reciprocal and write negative 4. Now we need to find the derivative. So what we are going to do first is to find the derivative using the power rule, 2t plus 1 to the power negative 4. Then we find the derivative of 2t plus 1, then multiply both together. Again, the main reason, because this is a composite function. So here we can see we get negative 4, 2t plus 1 to the power negative 5, because negative 4 minus 1 is negative 5. Then the derivative of 2t plus 1 will give us 2. So our final solution will be negative 4, 2t plus 1 to the power negative 5 times 2, which will give us negative 8. We can change the negative 5 to a positive exponent by bringing 2t plus 1 as a denominator down. So the final answer will be 8 over 2t plus 1 to the power 5, and it's negative. Now, let's look at the theory behind the concept of chain rule. So here, as we said earlier, suppose you are asked to differentiate the function f at x equal to square root of x squared plus 1. Again, we cannot use the previous rules that we follow. We cannot use only the power rule, and we cannot use only the sum rule, because this is a composite function. So the concept of a composite function, let's assume square root of x squared plus 1 is a function of lowercase f at x, or let's use the term f at u. So we will say that f at u equal to square root of u is x squared plus 1. Then u equal to g at s will be x squared plus 1. So in order to find the uppercase f at x, we are going to have f composite g. Now, to find a composite of a function, as we said straightforward, we find the derivative of f times derivative of g. And that is what we call the chain rule. So here we say, turn out that the derivative of a composite function, f composite g, is the product of the derivative of f and g. So this fact is one of the most important of the differentiation rules, and it's called the chain rule. So this is the whole concept here. So we can use this formula to find, again, in this case, uppercase f is a composite function. So the derivative of a uppercase f composite function, it will be f at x, g at x times g at x. So f at x argument will be g at x. Then we find the derivative. So let's see the example again. So here to find the derivative of square root of s squared plus 1. First, we use the power rule to find square root of s squared plus 1. Then we multiply by the derivative of s squared plus 1, which is what we said, a g at x. So that's what we have here again. So we can see first we find the f at x first, f at u, derivative. So it will be the power rule half u to the power half minus 1, which will give us negative half. So the final answer here will be 1 over 2 times u. Then we find the derivative of s squared plus 1, which gives us 2x, which will be our derivative of g at x, 2x. Then we multiply the 2. So we have 1 over 2 square root of s squared plus 1 times 2x. And 2 will cancel each other, so we get x over square root of s squared plus 1. Now, let's go through the steps here one more time. There's another way we can solve this problem by using a formula. The formula will be dy du times du dx. This tells us that, okay, let's find the derivative of s squared plus 1, the square root. So that will give us 1 over 2, again, because here we say y equal to square root of u. So the derivative of that will be half u to the power negative half. So we'll write 1 over 2 square root of u times the derivative of u, du dx, which is, again, our 2x. We find the derivative. S squared plus 1 will give us 2x. Then we multiply the 2. First of all, we know u equal to what? S squared plus 1. So we place it. Then we get the same solution. So the same thing, we can apply the chain rule to almost any function, including trigonometric function. Now, we already learned all the rules. For example, power rule, product, sum, quotient, tangent functions, exponential rules, log, etc. So now, if we have a problem and we look at it, for example, this example here, when we look at it, it seems this is, for example, if the question is s squared plus 1, then we know we use the sum rule straightforward. We can use the power rule here. But here we can see that this is a composite. So when it's a composite function, that's where we have to use the chain rule. So example here, y equal to sine u, where u is a differentiable function of x. So this means we have a composite function. Then we can write dy dx equal to dy du and du dx. Now dy du, the derivative of sine u, will give us cos u. Then whatever u is, we find the derivative of it also, so du dx. Here we can apply the dy dx sine u, give us cos u, du dx. Now, next here we can see, as we said earlier, the power rule. So let's say we have y equal to g at x to the power n. We can substitute f at u, g at x as u to the power n. So here we say u now is g at x. Now, using the chain rule, using the formula, we get dy dx equal to dy du, du dx. So first, we use the power rule because u to the power n will give us n, u, n minus 1. Then we have to find the derivative of n. So this is the concept of exponential function. So we will see an example soon. So the derivative of n will give us the u dx. And that will give us n, g at x, n minus 1, the derivative of this. Now let's look at the example here. So here we have y equal to x cubed minus 1 to the power 100. So first, we use the power rule to find the derivative of x cubed minus 1 to the power 100, which will give us 100 times x cubed minus 1 to the power 99. Then we have to find the derivative of x cubed minus 1, which will give us 3x squared. So here we get 100 x cubed minus 1 to the power 99 times 3x squared. Then we multiply 3 by 100, we get 300 x squared x cubed minus 1. Now, we also said the reason for the name chain rule becomes clear when we make a longer chain by adding another link. Like for example, we have dy dt. Now here's like a second derivative. So dy dt can give us, first we find the dy dx, then we multiply by dx dt. Then we find the du dx, and then dx dt. So now we have a chain of a dy, du, then du dx, then dx dt. So this is what came with the idea of the name. Now let's do the derivative of exponential functions, which we said looks similar to the example we saw. Because if we have 2 to the power x, we can find the derivative. We can find the, let's say, we can find the derivative by using what? Exponential rule. So let's look at example here. So here we say we can use the chain rule to differentiate an exponential function with any base, as far as the base is greater than 0. So we know, for example, a equal to b to the power natural log b. So b should be greater than 0. So b to the power x is equal to e to the power natural log b times x. And then the chain rule will give us, for example, to find the derivative of d dx bx. We know bx is what the value given us, so we get d dx e to the power natural log bx. So this means first we find the derivative. If we remember, the derivative of e is the same thing, or e to the x is the same. So here the derivative of e to the power natural log b times x will give us e to the power natural log bx. Then we find the derivative of the exponent. Now, the derivative of y to the power x will give it ex times the derivative of x is 1. So that's why we say derivative of ex is the same as es. But here, to find the derivative of natural log b times x is not 1. So we find it. So that's what we write here, d dx, natural log b and x. So we write down our first solution, e to the power natural log b times x. Then the derivative here will give us natural log b. So the final solution will be, again, we said this section will give us b to the power x natural log b. Because b is a constant, so we have the formula d dx bx equal to bs natural log b. Now, for the derivative of each of the function here, let's say here they give us, find the derivative of g at s equal to 2 to the power x. We can use the formula, the derivative of g at s will give a derivative of the d dx 2 to the power x. So first we write our derivative 2x times what? Natural log 2. And d dx to the power x can give us roughly 0.693 times 2x. Natural log 2 gives us this, because natural log 2 again is 0.693147. So still we are using chain rule here, as we can see. Now, if it's x to the power 2, of course, the exponent is a constant value. So s to the power 2 will give us 2 times s to the power 2 minus 1. But here, remember, the exponent is a variable. So we have to use a chain rule. So that's another example here. So we have to find the derivative of 5x squared. So we say derivative dx 5x. Again, the exponent is variable, so we have to use the chain rule. So first, we find the derivative of this. So we get 5x squared. Then we get natural log 5. 5x squared natural log 5 times the derivative of x squared, which will give us again 2x. So our final answer will be, and the 2x is here, the 5x squared, the natural log 5. And that will be the final solution. So again, to find the derivative of 5 to the power s squared, we use the chain rule. So we have the 5s squared first, times what? The natural log 5. Then the derivative of s squared, which will give us 2x. So that will be the conclusion of this chapter. Again, in the future, we are going to do more examples. And see you then. Thank you.